Suppose that we can speed up Earth's rotation to such an angular velocity that an object on the equator starts to float in the air, or the gravitational attraction between Earth and the object is not able to provide enough force for the circular motion of the object. What is this rotation period t? Let the Earth's radius be r, its density p, and its mass m. So, if we think about this, if we have an object traveling in a circular path, let's say this is the center of the circle, it's going to have a centripetal force or radial force that's accelerating it towards the center of the circle to keep it in this circular orbit and stop it from flying off in direction tangential to its position. So it's this force that the gravity needs to be able to provide in this case. And basically, when you start floating, it's when the centripetal force required to keep you spinning in the circular path is equal to the force of gravity, which means that the force of gravity is providing all of the necessary centripetal force or radial force. And there's just no gravity left to keep you on the ground, so you start floating. So this is basically what's happening. And then, if you remember from Newton's second law, that says that the summation of all of the forces, or net force, is equal to the mass times acceleration. You can say that the radial force, or centripetal force, is equal to the mass times the centripetal acceleration, which is also equal to the mass times the radius of the Earth times the angular velocity squared, or omega. This symbol is omega, not W. So that is this quantity, where the centripetal acceleration is this quantity right here. And that is the centripetal force. Now we need to figure out the gravitational force. So the gravitational force is equal to the gravitational constant times the product of the two masses. I'm going to call big M the mass of the Earth, and little m the mass of the object, or u, or whatever is on the equator. And we're going to divide that by r squared, which is the distance between the centers of the two objects. So if this is an object on Earth's surface, its center is simply going to be on the Earth's surface if it's much smaller than the Earth. And the center of the Earth is going to be like here in the middle. So its distance is the radius of the Earth. It's W squared, or omega squared. And since this problem doesn't provide it, I'm going to write down a few things. The gravitational constant is equal to 6.67 times 10 to the negative 11. And I'm not exactly sure what the units are, so I'm just going to leave it like this for now. The mass of the Earth is approximately 5.972 times 10 to the 24 kilograms. And the radius of the Earth is about 6.356 times 10 to the 6th power meters. So that's our quantities that we can use later. So now that we have this, going back to our original equation, we can say that the mass of the object times the radius times omega squared, or the angular velocity squared, is equal to the force of gravity, or the gravitational constant, times the product of the two masses divided by the radius squared. Now if you notice, the masses cancel out. The little mass cancels out. So the object on the equator's mass will cancel out. And this is referring to the object on the equator's mass, because it is the one that requires the centripetal force to stay in the circular orbit, not the Earth itself. So we're left with this, and then we can say the angular velocity is equal to the square root of g times product times mass of the Earth over r cubed, or the radius cubed. So I'm going to erase this to make more space. And if you remember, the angular velocity is equal to 2 pi over the period t. So we can replace that here. So 2 pi over t is equal to the square root of gm, gravitational constant times mass of Earth, divided by the radius of Earth cubed. So that becomes this. And now we just solve for t, which gives us 2 pi times the square root of r cubed over the gravitational constant times the mass of the Earth. And we can just actually just use this equation. We don't even need the density. But if you want the density is equal to the total volume of the Earth divided by the total mass of the Earth, which, if we assume that the Earth is a sphere, is 4 over 3 pi r cubed over the mass. And then you can substitute that back into here to find another equation, which I think is period equals the square root of 3 pi over m over gm or something like that. I'm not exactly sure, but if you want to use this equation, you can. And that involves the density. So you're going to have like a density in there somewhere. But that's another equation that you can use. But it's really not necessary to derive that. And we can just use this equation right here. So this becomes 2 pi times the square root of the radius cubed, which is 6.356 times 10 to the 6 meters. Cube that, and then divide that by the gravitational constant, 6.67 times 10 to the negative 11 power, times the mass, 5.972 times 10 to the 24th power kilograms. This is a little bit squished, but just know that that is this value here. So now we just need to simplify this. So this gives you about 5,044.67 seconds. But this really doesn't mean anything since we're not used to seeing that many seconds. So we can actually convert that to hours. And that gives you about 1.4 hours. So given all of that, let's erase everything here. The period required for you to float at the equator is 1.4 hours, which is really fast, and we're not going to get anywhere near that. So basically this is like you're having a day every 1.4 hours, and if you're standing at the equator, you would be able to kind of float in the air, and that is how you would solve this problem here.